So we left off last time with a kinematics problem, and I wanted to do one more of those problems. Not that it's going to be all that much different. The process will be exactly the same, but just a little more practice in this process before we move on to kinetics, which is really our last section in this class. So looking at this problem here, we have an arm AB. You could think of that as the throw on a crankshaft if you wanted to. Then the arm BC. That would be the connecting rod on a crankshaft, and finally this slider C. You can look at this in all different types of contexts, whether it's in an engine. You could even think of that if C was an athlete's foot and CB was the lower leg and AB was the upper leg. If you're trying to do some dynamic analysis on an athlete running or doing some kind of activity or something. So we'll apply these skills that we're learning to all kinds of different things. Well, if we're looking for the acceleration of block C, if we're told that this arm AB is rotating this way, I think most people would recognize that the slider C is going to be going down. It'll have an acceleration down. It'll have a velocity down. If I am wrong in that assumption, I just get a negative sign. But let's start out then with the equation that the acceleration of C is equal to the acceleration of B plus the acceleration of C with respect to B. Okay, is that true? Yeah, that should get us the acceleration of C. Yes? This angle up here? 30 degrees. 30 degrees. So when I used to do partial credit tests, a lot of times students would write down that equation, and yeah, that's the governing equation for the problem, but that's just the beginning of this thing, right? So our task is to figure out all of these pieces. The acceleration of B is really going to be broke out as the acceleration of B in the normal direction plus the acceleration of B in the tangential direction. And then I'm going to break up the acceleration of C with respect to B. So that would be a little bit like standing at point B, an observer at B, watching what's going on at C. And we would again break that into a normal and a tangential. So we could talk about the acceleration of C with respect to B in the tangential direction plus the acceleration of C with respect to B in the normal direction. So as we're honest with this and start to expand those terms, we start to have more and more terms. And then our trick is going to be to put the pieces into each one of these. If we look at a standard XY coordinate system, so why don't I put my coordinate system over here? I'll say that this is the X direction, that's the Y direction. This normal piece will probably have two components. The tangential piece will probably have two components, and so forth. So we'll have a lot of stuff going on here, but I think we can get through it. So with that, maybe we should say, what's the, if I look at the acceleration in the tangential direction, isn't that alpha times r, is that right? If I look at just the magnitude. And the acceleration in the normal direction, what's that? I mean, v squared over rho, although I don't know that we'll use that one. What about omega squared times r? I mean, yeah, omega squared times r. Does that work? Yeah. And remember, if we have a vector expression, then we talk about the vector expression, that the acceleration in the normal direction in a vector expression, we like minus omega squared times the vector r. So we'll be using all of those. Okay, let me go ahead and assume then an alpha and omega here. So I'm going to talk about an alpha CB, and I'm going to talk about an omega CB, and we're going to assume these. Okay. Again, you might say, well, why'd you pick clockwise? Oh, I don't know. Seems reasonable. I guess that's counterclockwise, isn't it? So that seems reasonable too. Okay. Pick counterclockwise. If I pick the wrong direction, we get a negative sign, right? Not a big deal. So with those, let me start to write out this equation. More terms here. I'm going to say that I'm going to talk about minus the acceleration of C, and I'm going to write that in the magnitude, and then I'm going to say that's in the j direction. So I've assumed that this acceleration is down. So that's in the minus y direction. That's the minus j direction. If that's wrong, I'll just get a negative sign for that magnitude. And I'm going to set this equal to the acceleration of b in the normal direction. Well, if I come down and look at this link AB, let me reproduce this here very quickly. So if we look at this having some omega AB and alpha AB, if I look at the normal acceleration, that's going back that way. There's the normal acceleration of B in the normal direction, which is going to be what? Omega squared times r. And then how about the tangential? Where's the tangential acceleration? There's the tangential acceleration of B, which is going to be what? Alpha times r? Okay. So let's see, what directions is that going to have? If I start to break those up, I'm going to say that this angle in here is what, 30 degrees? Is that right? And what angle is this? Well, it's going to be at a right angle to this. So if I were to come up here and draw a right angle, there's a right angle, then that puts me at what with respect to the horizontal? 60? All right. So I've got 60 degrees back here. So I think that should help me. So now I can talk about the acceleration of B in the normal direction. That would just be the omega. What do we have for omega? 3. So 3 squared, that's my omega squared. And what's the distance? 0.5. And then I have to break that up in terms of a minus cosine 30 in the I direction plus a sine 30 in the j direction. Is that right? Yeah, the j should be positive because it's up, and the xp should be negative. So I'm breaking this vector here that looks like that into a horizontal and vertical. So that's that. We're good with that term? So then we'll add to this. I've done this piece. So now I need to do the tangential. What's the tangential? Alpha. What's alpha on this thing? 5? 5 times r, which is 0.5. Times now I need to get the direction for r. I mean, I'm just multiplying that through. So what am I going to have there? Minus 60. No, not, let's see, 0.5. Did I do that right? I guess it's cosine of 60, isn't it? Yeah, so minus. So minus the cosine of 60. And that would be in the I direction. And then minus the sine of 60 in the j direction. Is that right? If I break this one up, it's going that way and that way. Both pieces would be negative, wouldn't they? Yeah, I think we're okay with that. Okay, so I've done that piece. And then to that I have to add what? Well, I need to start to talk about this, the acceleration of c with respect to b. So you're going to place yourself at b, you're going to stand at b, and you're going to observe what's going on at c. So it'll have a tangential piece, which would be alpha CB. And what are we going to have there? Alpha CB, if I use the right-hand rule, is alpha CB positive or negative? If I wanted to write this in a vector form, you take the fingers of your right hand, put those in the direction of that's rotating, counterclockwise, so your thumb's pointing out of the paper, isn't it? Out of the paper is positive z or positive k, isn't it? So I'd say that this was positive. I'll leave this positive over here. Positive in the k direction, and I'm crossing that with what? I'm crossing that with the R that goes from B to C, right? There's the R. So how do I get from B to C? Well, it's going to be minus 0.6 sine 45 in the I direction, minus 0.6 cosine 45 in the J. Is that right? Yeah, both of them should be negative because it's down and to the left. I think we're okay with that. Good. So that took care of that one. And then lastly, I have this normal piece. So I've got to add one more term here, which is going to be this minus omega CB. So omega CB squared. And the negative is not in the inside the square. So minus omega CB squared, and then I simply have to multiply that by the R vector. So I'm going to multiply this by minus 0.6 sine 45 in the I direction, minus 0.6 cosine 45 in the J direction. Okay, so if I account for the unknowns here, I have this unknown, I have this unknown, and I have that unknown. This is the one that I'm really looking for. This one often shows up. When I separate the equation into i's and j's, I'll have two equations, so two unknowns don't bug me, but this unknown does bug me. This is a problem. So I'm going to have to come up with that. And how do we come up with that? Use instantaneous center, right? Okay, so take a little time out from this. We'll move on to similar picture here. So we're going to find omega CB with the instantaneous center. Okay, so if I look at this, and this is just a reprint of the picture here, I'll draw the instantaneous center for this link here, CB. See what that looks like. And the velocity at B is going to look like what? It's going to be perpendicular to that, isn't it? So it'll look something like this. So there's the velocity of B. And how about the velocity of C? It's constrained to the bore, so it should be straight down, shouldn't it? So there's the velocity of C. And I put a perpendicular here, and then I'll put a perpendicular here. And there is my instantaneous center. Okay. Let's see, I can work out some geometry here. Well, do I know what the velocity of B is? I definitely don't know what the velocity of C is. The velocity of B, I could say, well, let's see, in general, velocity is equal to r times omega, isn't it? Do I have an omega here? Yeah, 3. So I could say that the velocity of B would be equal to that 3 times what? 0.5? Okay. So 1.5 meters per second. So that's the velocity of B. Now I could get the omega for this whole thing, because this is going to have some omega like this, and that in fact would be my omega CB. That's what I'm looking for. That's what I want. Well, if I knew this distance here, I could get that, couldn't I? So let me talk about this distance D1. I need some geometry from this. Let's see, what's this angle here going to be? Should be the same as, I mean, if I were to come over and put this IC on this picture here, sometimes that helps you a little bit. That angle's the same as that one, isn't it? So if this is 45, that has to be 45, so this is 45, isn't it? Okay. And let's see. This angle is 30. So if I come up here, if this is a right angle, this is 60. That's 45. So that makes this what? 180 less 60 less 45. Is that right? So 75. Okay, so now if that's 75, I can say that this included angle in here has to be what? Wouldn't that be 105? Yeah. I could have 105 there, wouldn't I? We're okay with that?
Where 180 less 60 less 45.
Mm-hmm.
That comes from the angles on this bar.
That comes from this being a straight line here.
Okay.
So I take this one and subtract. Whoops! No, that gives me the. No, that's not making sense, is it? Because I'm clear back around there, aren't I? So this would have to be. No, this is 45 in here, isn't it? Yeah, so I'm good. 180 less this 60. This would be 60. This is 45 because that's 45. Yeah. Yeah, I think we're okay now. Yeah. So I think we're okay with 105 now. We're good? Okay. So that means, let's see, that this angle in here is going to be what? 30? Okay, so we got 30 there. So we could say that D1 was to the angle opposite it, which is sine of 45, as this side here, which is 0.6. 0.6 is to 30 degrees. Sine of 30. There we go. Sine of 30. So I can come up with a D1 here. That turns out to be 0.8485 meters. So I can say then that omega CB is going to be equal to, I mean, we go up here in our general equations, omega is equal to velocity divided by r, right? So I take this velocity, which was 1.5 from up here, and I'm now dividing this by 0.8485. So I come up with 1.768 radians per second. I've kept quite a few significant figures here. If you don't keep this in the memory of your calculator, I'd use at least 3 or 4 significant figures so you don't get round off, or as much round off. Questions so far with that? So that's our omega CB. We're going to take that back to the previous calculation. Let's see. Yeah, that's 75, isn't it? Right. Okay. Okay, so we take this back. We get omega CB at, we put this in here. We now know this value, 1.768. I have to make sure that we square that. So I'm not going to, the last problem that I went through on this, I actually did the crossing. You want me to do that on this one, or you okay with it as is? I guess I can do it. So you're going to have minus the acceleration of c in the j direction is equal to 4.5. Is that right? 9 times 0.5, yeah, 4.5 minus 4.5 cosine 30 in the I direction, plus 4.5 sine 30 in the J direction, plus 2.5. 5 times 0.5 would be a minus cosine 60 in the I, and then another minus 2.5 sine 60 in the J, and then I get into the crossing business here. So we'll have K crossed with I as a positive J, isn't it? So we retain the negative sign, minus alpha CB times 0.6 sine 45, and that is K crossed I is J. So then this one, K cross J, is a minus I, so that will cancel with that one. So we will have a positive alpha CB times 0.6 times the cosine of 45. K cross J is minus I. Okay, and then we're going to have a minus. What's that thing squared? So let's see, a minus and a minus gives me a positive. And then when I square this and multiply it by 0.6, I get 1.875. 1.875 times the sine of 45 in the I direction. Negative, negative is positive. Then I'll also have a positive. Same thing, because that's 0.6. 1.875 cosine 45 in the J. So that's your equation right there. Questions with that? So, like we said on the last problem, not particularly difficult, certainly tedious and long. You would equate the I's and J's at this point. Equate I's and J's. And that's going to give you two equations and two unknowns. With the two equations and two unknowns, you can solve for alpha CB. Alpha CB turns out to be equal to 9.01 radians per second squared. It's a positive number, so that means indeed it's going in the counterclockwise direction, we assume. And then last but not least, see if I can fit this in here, the acceleration of C turns out to be 2.41 meters per second squared. That's also a positive number, so which direction is that going? We assumed it is down, didn't we? So indeed it is going down. Okay. So lots of pieces to a problem like this, but if you're careful, you can get through it pretty well. Yes?
So since the acceleration is only in the J direction, if you were to go through this and solve all of it, would we find that all the I pieces equal zeros?
Right. There is no I acceleration for C. Other questions? Okay. So you've got some homework problems like that to practice on. Are you going to find one of these on the final? Probably. You can break this up and put it on a final pretty easily, right? There's lots of little pieces here. This is a great finals question right there, right? Then with that, you can come back here, start to put it in. So, yeah. I'd make sure you're ready for one of those. Yes?
So how do you get the acceleration in the C direction?
The acceleration in the C direction? Right here? This one? How do I get that?
After you get the, oh, wait, never mind.
It's just going to be two equations and two unknowns. Okay. I can go through that if you want. That's good. No? Okay. So we're going to look at our last section. We're doing pretty well time-wise in here. The last section is rigid body kinetics. We're going to keep this mainly plane kinetics, two-dimensional. The progression of this is exactly like our work in not rigid bodies, but a point. Remember, we spent a lot of time in Chapter 12 dealing with kinematics of a point. And then we started talking about kinetics. So we've spent quite a while talking about kinematics of a rigid body. And now we're going to go into kinetics. And if you remember when we went to Chapter 13 from Chapter 12, we all of a sudden started talking about Newton's second law, where force is equal to mass times acceleration. And that's really all you need if you have a point. Everything it looks like this. You're approximating it like this. But if you start looking at a rigid body, where you have some mass center, let's say, this thing could all of a sudden be rotating, right? I mean, if a point's rotating, that doesn't make any difference. But if this thing starts rotating, that makes a big difference. So we need another equation. And our equation is going to be that the moment is equal to I times alpha. Okay, where alpha, of course, is the same alpha that we've used. That's the angular acceleration. And I is the mass moment of inertia. Okay, so this is the mass moment of inertia. Which is really analogous to mass. Remember, mass was the resistance to velocity change, or maybe being more specific, the resistance to velocity change in a linear sense. Well, I is going to be the resistance to angular velocity change. So if we have something that's rotating and it has a high mass moment of inertia, it's going to be hard to change that rotation. So for instance, a flywheel, we like that to continue rotating at a fixed speed. So we're going to try and design it so it has a high mass moment of inertia. Now, let me say what the units are. It's kind of spoiling the surprise here maybe, but the units on this are going to be mass times distance squared. Okay, so some really common units would then be kilograms, meters squared, or slugs, feet squared. Okay, and you can have some, you can put inches and things in there. You have to be careful of that. But those are a couple real common ones. So what this really tells you is how some mass is distributed around some centroidal axis. So if I look at, let's say, a flywheel, and I have a couple options for making this flywheel. If I were to cut this flywheel through the center, it's on some shaft like this and maybe rotating like this with a alpha and an omega. And I look at this thing, so I take this section here and look at section AA. I have some options for section AA. If this is the center line here, so talking about that center line, I could maybe build it like this, where I just take a chunk of steel, cut it out, put a hole in it, the center line. That's okay. Or I could design it like this. Maybe it would have the same weight, but I'd concentrate a lot of this weight at the outside ring here and have a thin section here and concentrate a lot of this weight out here. Okay, and we'd say that this might have the same mass that this has. And I could, maybe if we're playing around with this, we might try one more. Maybe we make a really heavy hub here, like this, and have this, you know, the dreaded saw blade, like that. You can imagine those might all have the same mass. Okay. Which one's going to have the greater mass moment of inertia? Well, the mass moment of inertia, and this is the one you talked about in physics, right? I mean, if I want to be careful with this from statics, we talked about the area moment of inertia. Which was how the area was distributed around some axes, right? And the units there were length to the fourth power, inches to the fourth, feet to the fourth, meters to the fourth, or something like that. And that's where you have to read this in context. I think last term in physics you dealt with mass moment of inertia, right? Didn't things have these units in physics? Yeah. So we're not talking about these. We'll come back to that spring term in strengths and materials. Conceptually, it's very similar, though. This gave us an indication of how the area was distributed around some axes. This is going to give us the measure of how mass is distributed about some axes. So which would have the largest mass moment of inertia? Probably this one, because its mass is further distance from that axis, right? If we go back and we look at how this is calculated, we can say I is equal to the integral of r squared dm. So I mean, if I have some body here where we have some differential element of mass and some axes here, we could talk about this r distance. There's r. There's dm. Or we could say I is equal to the integral of r squared dm. Sometimes they'll call this the second moment. Okay, and it won't be till next term we actually talk about the first moment. So this is why oftentimes our flywheels have a very heavy rim and then a lighter center, because that way we can put the mass further distance. For instance, this little chunk of mass here, or this little chunk of mass there, or that little chunk of mass there doesn't do much good when you're thinking about squaring r, right? So that's why we try and concentrate the mass further distance out. So this is going to be a much better, it's going to have a much higher I, which is good if you're not wanting to slow down. It might be bad if you're having to accelerate it. Questions with that? Well, I don't know if you talked about the parallel axes theorem in physics, but let's say that we want to transfer this to a different axis. We can. So let's say that we have some body here. We'll say that we have an axis, and this is through the mass centroid. Okay. And then maybe I have another axis over here that's parallel to it. And we'll say that these are separated by some parallel distance d. We'll say this is the OO axis. So the parallel axes theorem says that I about OO is equal to I about the mass center, plus the mass times the distance squared. Okay. So this is a hot spot in the middle of the paper, isn't it? I think it's coming in through somewhere there. So the thing you have to be careful of is this value here has to be through the mass center. Okay. Do the units work out on this? I mean, if this has units of what? Distance squared times mass, what's the units on this going to be? Distance squared times mass, right? So the units work. And like I said, the one thing you have to be careful of is this always has to be through the mass center. So for instance, if you had this axis here, could you transfer this axis directly to that axis there? No, you couldn't with the parallel axes theorem. You'd actually have to use the parallel axes theorem twice. You'd have to transfer it to the mass center, and then from the mass center, you could go to that axis there. Okay. So the parallel axes theorem can be kind of handy, because if we maybe all of a sudden we've calculated the mass center, or the I about here, and you'd like to now think about rotating it through there, you can transfer that with the parallel axes theorem. Questions with that? Where do we use things like this? And I've used the term flywheel. What's that mean? Is that the best ride at the amusement park? Connected to what? Where do we find the flywheel? To the transmission. Yeah, it sits between the engine and the transmission, doesn't it? Okay, and why would we want such a thing? Okay. Oh. Okay. Yeah. 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 I mean, it helps to hook the transmission to the engine. Probably the biggest thing is if we look at the engine, most engines are 4-stroke, and we'll talk tomorrow about 2-stroke engines, a 4-stroke engine. But let's say 4-stroke engines. Most of you came to school today in something that was propelled with a 4-stroke engine. So a 4-stroke engine is producing, if I have a single-cylinder engine that's a 4-stroke engine, it's producing power what percent of the time? 25% of the time, right? Okay. So let's keep things really simple and think about your lawnmower starting to get spring. Things are greening up. Got to drag out the lawnmower, right? You got a lot of lawnmowers. If you got a push lawnmower, single cylinder. Okay, so we got a single cylinder 4-stroke engine on that lawnmower. It's producing power 25% of the time. Well, I like to mow grass 100% of the time, right? So how am I able to mow grass that other 75% of the time? It's with the flywheel, right? Okay. And as we'll see tomorrow, I mean, as we go through the cycles in the 4-stroke engine, that flywheel not only continues to cut the grass during that time period, it actually drives the engine during that time period. The compression stroke is made possible by the flywheel, right? Yeah. So if we start to lighten up the flywheel, it will begin to run quite rough and whatnot. Now, if you've ever taken apart a lawnmower, you might find out there's no flywheel in this thing. So did I not learn my this right in the dynamics class, or what's going on here? The blade itself, absolutely. If you turn the lawnmower over, and please turn it off before you do this. Yeah, I mean, when I was a kid, you'd leave the lawnmower on. You didn't have all the little switches and whatnot. So even if you go in the house and get a soda or whatnot while you're mowing the yard, you could just leave it idling. But anyway, they usually turn off. But if you're going to start to investigate the lawnmower, be careful. If you turn it over, it's got a great big blade on there that's spinning around. Does that work as a flywheel? Yeah, absolutely. As that blade is spinning around, if you take the blade off, it's not going to cut grass, and it probably won't even run. And in fact, if you decide, well, that string, I'm going to give it the old sharpen job here, and so I sharpen off this side and I sharpen off this side. Maybe I'm a little too aggressive over here, and I cut off more on that than the other side there. It's out of balance at that point. And what's it going to do? Make it not run very well. Okay, that's why you got to be kind of careful with that. You may want to rebalance that blade. So we see this in a lot of places, and not just in engines. If you think about things rotating, even in an earthquake situation for your structural engineers and whatnot, this comes into play. So when we get together next time, we'll talk about more about engines, putting this into context, and also continuing on with these calculations. Take care till then.